Hello, hello. All right.
Good morning, Professor.
Good morning. Thank you, Sydney. Awesome. Or good morning. I think was that Sydney? Who was, can I ask who that was that Sydney? I'm sorry. Well, anyway, good morning. Good morning. Okay, awesome. And good morning, Sydney. Either way, good morning, Tree. Good morning, Loani. I'm just looking at that. Good morning, DJ. Wait, I saw good morning, Sharon. That's good morning, Sarah. Good morning, Munera. Okay, I'm going to the chat. Um, I'm going to the chat. Good morning, Ashley. Good morning, Sharon for the double. Good morning, Sarah for the double. Munera for the double. Good morning, Lena. Good morning, Sydney. Good morning, Haley. Good morning, Emily. Good morning, Pushpita. Good morning, Tree for the double. Good morning, Loani for the double. Good morning, DJ for the double. Good morning, Maya. Does someone want to admit in direct chat who it was that said hello with their voice and got a triple or got point? I'd love to know. Just tell me in the direct chat. But okay, I'm going on. And we're gonna get roll. Oh, good morning, Kyla. Okay, I think it was okay. Oh, that's multiplayer co-op. That is totally multiplayer co-op. All right, awesome. All right, I also have to ask you, we're just going to good morning and good morning, Erica. Awesome. Okay. We're going to I will switch the view. You didn't. Oh, okay. All right, fair enough. Well, that's honest of you. That's also multiplayer. In a way, that's multiplayer co-op because you're somehow making the space for someone else to get. Does someone want to take credit for that? All right. Well, anyway, I mean, I appreciate it. Okay. So we're gonna get rolling. I want again. What's on the board is the ultimate. So we want to finish. Well, I say finish. We want to get an answer to question 9 today. That's the main goal. Now we're going to get an answer. We're going to do a quick thumbnail of like how we get there, a quick thumbnail of how you could get there on your own. But then believe me, that opens up a whole topic that opens up the first real new topic of this course. So there's going to be expansion, believe me, next week. I'm saying question 9 represents a larger way of thinking, a larger mathematical and scientific analysis. That's very important. And everything in the last couple of classes, all the prior questions are somewhat review, somewhat refresh and recollect, but they're all building to this question, to the topic that is crystallized by question 9. So what I'm trying to say is the goal for today is to get an answer to question 9, to get it, to see a way of understanding how we get that answer, thoughtfully without just copying something down that we don't understand. But then we're going to back up. We're not going to back up on homework 1A, but next week we're going to really unpack more and more what the implications of this, what the implications are. And when I say with the implications, I mean the mathematical implications. So that will lead you to homework 2, the math methods homework that's due in a few weeks. But what I'm saying is, even just based on what we do today and finish today by the end, you should have enough to start seeing how to dive into, not just homework 1B, but homework 2, and start doing these exercises that are mathematical in nature. Okay, you get the point. So we're gonna try, so we're gonna finish homework 1A today. Get an answer to question 9. And the thumbnail sketch of that is here written on the first page of the board. But I will switch the view on the screen, but you're gonna do me a favor first, because I'm still getting used to the schedule, as are you. You're gonna remind me, please, exactly how far we got 2 days ago in going over homework 1A. In other words, what I don't remember exactly, did we finish? I don't believe we finished. Did we finish question 4 in your class, or um, from the homework 1A? Or we stopped at the beginning of question 4. Thank you, Tree. Okay, okay. No, thank you, Eric. Okay, so in fact, right here. Oh, yes, right. This is yes, you're right. Okay. So this last line of the board right here is where we stopped. And good morning, Alice. Thank you. All right, awesome. Okay. So yeah, thank you. I see where we are now. Okay, okay. So I'm gonna try to do this somewhat quickly. I'm looking at the time. Okay, so where we were right before the end of question 4 2 days ago is I was saying accelerate net force is not constant with respect to position. Actually, what I should be saying right here, the net force does not equal a constant. It's changing from position to position. Therefore, we consider work and energy. What work is the integral of force with respect to position. Um, and the point of, and so you consider work whenever the force is changing from position to position in physics. So what work is the accumulated effect of, what did I just say? What work is, by definition, is the accumulated effect of force throughout a displacement, throughout a region of space. You push something through a distance or you pull something through a distance, and the accumulated effect, the accumulated impact of the force being distributed throughout that space is what we call work. So it's the integral of force with respect to space, to displacement. That's what it is. What's the point of it? What does it do? What does work do? It transfers energy, kinetic energy. Okay, so this is like a quick review, right, of last semester, but a reminder. So you might want to write this in English. We said this last semester, but work is the transfer of energy. Energy is the ability to do work, right? Energy is the commodity. It's like money. Work is the transaction. I mean, work is the activity. It's like a transaction. So when I do positive work on you, I give you kinetic energy. Where does the kinetic energy that you gain come from? Me. I lose kinetic energy, you gain it. That act is called work. Both work and kinetic energy are measured in the same units, joules. So if I do 3 joules of work on you, i.e., if I push you 3 newtons with 3 newtons of force through a meter of space, if I do 3 joules of positive work on you, then you gain 3 joules of kinetic energy. I lose 3 joules of kinetic energy. That's the idea. And kinetic energy, so if you have kinetic energy, that means you're big and you're moving fast. That means you have the ability to interact with something else and change its motion, right? I mean, that's the quick summary. So kinetic energy is always in this class, kinetic energy in English is the ability to do work by virtue of motion. Mathematically, it's always 1/2 mv squared in classical physics. Kinetic. So if you want to memorize anything, that you can memorize. Kinetic energy is always 1/2 mv squared. Your 1/2 mv squared will change once something is doing work on you. Okay, so that's a quick. Okay, so that's a concept. Now, again, I want to also make clear. I'm trying to review this and put this together. So I'm gonna like sort of say a lot. I'm not suggesting that that everything I'm saying here in the class, that everything I'm saying you'd have to write down for step 3 in the homework. I'm not saying that you have to write down everything. I am saying this though, as far as self-sufficient documents are concerned. Oh, good morning. Good morning. Awesome, Jory. Good morning. I'm saying you want to follow my model. Like you want to follow my model. Like you don't say things the way I'm saying them, the way I understand them. You want to eventually understand them and then say them the way you understand them, right? But notice I'm going top heavy. Like the first time I introduce a concept, even this semester, even if I feel like you've already seen it last semester or whatever, the first time I'm introducing a concept, I'm sort of over explaining it. That's what you want to do in your homework. The first time you're introducing work or energy in a document, over explain it. Make sure it's clear that you get it and that the reader can get it. Then once you have it, then you can just use it throughout the document. That's part of what we mean by self-sufficient document. You want all the tools that the reader needs to follow. You give them those tools. Then you can assume that they're using the tools throughout the document, the reading tools, but they've got to be given first, right? Oh, sidebar on this too. Now that you've all gotten your homework back, I believe, right? Let me say, I don't want to dwell on this. I want to stay with the physics. I think we've like really talked about the homework procedures a lot lately. But now that you've all gotten one back, first of all, reminder, do not, if you don't like the number you got, As long as it was more than half of the points, don't like stress it or consider it a criticism or anything like that. Just know that if you want, you can re-upload and get a higher number. That's okay. I think I keep saying that, but that means re-upload. Keep the old draft up and put a new draft up. All right, I think that's clear to everybody. Because everybody did well. I mean, really, the homeworks are good. Like, don't. Okay, I think that's good. But one little thing that seems to be a theme, I think, in this section, for whatever reason, maybe I didn't make it clear. I do need them to be PDFs. That sounds really picky. A lot of this sounds really picky, but they're much easier on my side to make marks on, and it's hard to explain why. But the Word docs, it don't work as well. They don't work as well. So please turn your document into a PDF, and for sure it needs to be one file for the whole document. I definitely can't have like one JPEG per page. That gets very confusing. Okay, so for some reason there were a lot of Word docs in this. I mean, you can work it out on Word, but then you have to print it as a PDF. That was the main thing, I think. Okay. So anyway, so work transfers kinetic energy. What work is force through space. Now, I'm going to say something I may have said to many of you if you had me last semester, but many of you didn't. So you may not have seen this before. Oh, yeah. So in fact, okay, I may have to stick a page in here. I want to tell you what I mean by a conservative force. Um, there's such a thing called a conservative force. In fact, okay, we're going to introduce a page here. Sorry, 1 second. Oh, sorry. Bear with me for a second. I'm sorry. I'm just sticking a page in. I don't, that got lost. Yeah, this is a lot of notes. Wait, it shows you. Yeah, well, all right. Bear with me. I apologize. Just don't want this. Okay. And I know someone's there. Someone's there. Okay. And what I'm writing right now is for you to teach you something. You don't have to put this in your homework. I want you to know it. Um, and so you can sort of tell I'm about to make a math point here. So that's why I'm sort of shifting it. Like you could say this is a sidebar, whatever. This is like a teacher sidebar. Um, And you can tell that it's a math, this kind of thing you can do in your homework. Like if I'm shifting to make a math point, like a GDP of math, I shift and say if y equals f of x. That's my way of saying I'm talking about math functions in general. They don't necessarily have to be physics statements. Teacher sidebar. Okay, just so you know that because there's a piece of notation that if you didn't, that you may not have seen before. If you have a general function of x, if we write this, if we write an integral with a circle on it like that, like not just an indefinite integral, but also not a definite integral with the boundaries on it, but instead we put a circle on the integral, that is a certain kind of definite integral that's called a closed integral. It's definite, but it's closed, and I'll show you what I mean. So this is a general math point I'm making. What it means is the integral from one point to another of the function plus the integral back From now on, if you see a circle on an integral, and it's very important in this class, we're going to see them especially in electricity when we get there. If you see a circle on an integral, it means a closed integral, which means an integral from here to there and back, like wherever there and here are. It means an integral over a round trip. Okay? That's a math thing. And it's a definite integral, but you get my point. So in physics, what we mean by a conservative force is any force that does zero work over a round trip. Or mathematically, in other words, like what I'm saying is this right here. I'm saying from now on, what we mean by a conservative force, FC, if F sub C, if you write FC, you mean a conservative force. And what is a conservative force? A conservative force is one that does zero total work if the force acts there and back. Okay? That's the definition of a conservative force. Now I'm going to very quickly, I'm going to say, if you're following me, it's very easy to think, sorry. Oh, yeah, sure. Like this, you mean? Is this what you mean? Yeah, okay, great. So I'll keep that up there so let me keep that up. So this math point I'm making, I'm saying if you integrate, if you integrate there and back for some function, that's called a closed integral. Like it's a round trip integral. Now I'm saying sometimes when you do that for certain integrals, for certain forces, by doing that, you'll automatically get zero all the time. But for others, you won't. And if you're thinking anything like, wait, I could sort of see how you would, but I feel like you always would if you're thinking something like, wouldn't you always get zero? Or if you're thinking like, I don't see how you would ever, then you're on the right page. You're with me. If you're a little confused and you know it, if you're like, I kind of get what he's saying, but I kind of feel like it should always be zero because you go there and you go back. The quick thing I'll say is think about this. With friction, for example, you wouldn't get, if you look the work done by friction, if you picture, like I'm pushing something along the ground, or I take it's hard to show you I just take like a book on my desk and I like push it so it slides across the desk until it stops, right? And then I pull it back. So I make a round trip or whatever. I pull it to the left and then I pull it to the right. If I just want to calculate the work done by friction on that book while it goes across the desk and then back, granted, my hand is also doing something, but just like one thing at a time, if I'm looking at the work that's done by friction, well, when the book is going this way, friction is going that way, right? When the book is going to the north, friction points to the south. So the displacement is, say, positive, and the force is, let's say, negative. So a negative times a positive is a negative. So on the way out to the north, friction does negative work on the book, like negative times a positive, like friction's going against the book's motion. So it's negative work. So of course, that's not a surprise. The book loses kinetic energy. It slows down and then it stops. Like no surprise there, right? Then if I pull the book back, granted, my hand's doing something now, but if we just keep looking at what friction's doing the same thing again. And remember, like now the book is going south, friction is pointing north, like they've both flipped, right? The book is going in the opposite displacement direction. The force is going in the opposite direction. So they've both flipped. So before it was like a positive times a negative. Now it's like a negative times a positive. So again, the friction's doing negative work. Like, right? Friction did negative work on the way out, but it's also doing negative work on the way back in. It's friction. It always does that. It always opposes your motion. It always tries to slow you down. Maybe other forces are also happening to like beat out the friction, but friction itself is always doing negative work, right? So for a round trip under friction, the total amount of work that friction does would be like, I'm just making up a number, like -3 plus -3. -6. I just made up the number 3. But do you see what I'm saying? That friction just keeps taking away from you, no matter if you do a round trip or not. And that's why if you do a big round trip, if I push this book across the table and then push it back, the table will heat up twice as much as if I just pulled the book along. right? Like more and more energy is sucked out of the system and like in the case of friction turned into heat, right? Now, if you get that, and I think you do, I mean, you can tell me if you do. Thank you. Right. Okay. Well, actually, okay. Yeah. If you get that, if you're like me, you could get that and be like, okay, that totally makes sense. Yeah, I see that. So it's like, so it's not zero. I would have thought the total work would be zero, but I guess it's not because friction flips its direction just like the displacement flips its direction. Okay, I see that. But then you might be thinking like me, but then why isn't that always true then? Like, all right, so it's never zero, right? But no, but now look at gravity. Look at gravity. If I throw something up under gravity and then it comes back down, on the way up, the thing is moving up, but gravity is pulling down. So you got displacement positive, force negative. So on the way up, gravity is doing negative work. It's slowing an object down. It's losing kinetic energy. The object slows until it stops. But then when the object comes back down, the key point here is that the object flips its displacement direction on the way back down. But gravity, unlike friction, does not change its direction. Gravity's always pulling down, always trying to get you to an equilibrium position that we call ground. So on the way down, gravity is in agreement with the displacement direction. So gravity does positive. It's like now it's a negative times a negative on the way back down. So gravity does positive work on the way back down. Right? It's just a question of the fact that gravity does not change its sign, but friction does. Friction's always opposing your motion. Gravity is always pulling you to a particular place. That is a subtle but huge distinction. Therefore, the summary of this is that gravity would do no work, net work, over a round trip. Whatever you lose on the way up, energy-wise, you gain on the way back down under gravity. Not true of friction, but yes, true of gravity. If work is the transfer of energy, what I'm saying when I say that gravity is a conservative force, I'm literally saying any energy it takes away from you in one direction of motion, it will give back to you if you come back and complete a round trip. It will always do that. So, gravity is what we call a conservative force. I'm going to tell you right now, I didn't put in notes. You can put in your notes, please. Here's the other forces that are conservative, like that do the same thing. Spring forces, i.e., the elastic force of a spring. So gravity is conservative. Spring forces are conservative. And the electrostatic force, which is where this whole sort of curricular ship is actually heading, or we eventually are building to and want to get to, is electricity, and magnetism. So the electrostatic force is a conservative force as well. So, all this stuff like fits together in the end. So I'm saying that if you want to make a list in your notes, like gravity, spring forces, and electrostatic force, or gravity, gravitational forces, elastic forces, and electrostatic forces are all conservative. Everything else, like friction, tension, normal force, all those things, non-conservative. Okay, so conservative force from now on means the total amount of work done for any round trip is zero. Therefore, the total amount of energy change is zero for a round trip. If the only forces doing work on if the only forces doing work on you are conservative forces, like even if there's more than one, even there's gravity and spring force, if you go on a round trip, your total amount of energy won't change. Therefore, I'm looking at okay. So right now, at this point in the discussion, or as of some point at the end of last semester, depending on like who you're, the only kind of energy I've ever even mentioned is kinetic energy. I'm saying work is the transfer of kinetic energy. But now we could say, oh, if there are these forces that do that, if there are conservative forces in the world, we can make up a concept to save ourselves a lot of headaches from having a lot of headaches. We can make up something called potential energy, which is like, okay, the bottom of the slide now, right? Potential energy. What it says mathematically is the potential energy that you have at any non-zero place, at any arbitrary location away from equilibrium, the potential energy that we say you have is a prediction of the amount of energy that the conservative force would give to you to bring you back while it brings you back to equilibrium. That's what it's saying mathematically there. In other words, let me back up and say, if you just made a list of conservative forces, technically a conservative force is one that obeys this blue statement. A conservative force is one that does zero net work around a round trip. But in your mind, like intuitively or informally, if you think about it, what all conservative forces have in common is they always have some kind of equilibrium position or equilibrium orientation associated with them. Like protons always want to be near other electrons. I mean, you know this from chemistry. Objects always want to be near the ground if they fall to the ground. And springs always want to be, unstretched or uncompressed. Every force that's conservative is a force that's trying to bring something to an equilibrium, right? So what we can say with conservative force is this: look, if you bring something away from equilibrium under the presence of a conservative force, if I hold this object up here above the ground, up here above the ground, right? I had to do all this work on the object against gravity to bring it up here. I had to do work, force times distance, mg times h, to bring it up to this height h. I had to do work, force times distance, mg times h, to get it here. So I did all this work, so I gave it all this energy. I'm giving it energy. It's moving, it's moving, it's moving. Now it's here. Well, I did all this work. I gave it all this energy, but now it's sitting here. It doesn't have any kinetic energy anymore. I could say that it has no energy at all, but I know that if I ever let it fall back down to where it came from, if I ever let it complete this round trip, I know that the exact amount of energy I know the exact amount of work that gravity is going to do on it to bring it back down. I know in advance the exact amount of energy that gravity is going to give it on the way back down. It's necessarily got to be the same amount of energy that I gave it to bring it up here, right? It's got to complete zero around a round trip. Or put another way, it's got to be the exact same amount that gravity sucked out of it. What if I just throw it up? I don't want to throw it but if I threw it up and it's slowing down to zero, whatever amount of energy it lost on the way up, it has to gain on the way back down. What is that? The amount of work that gravity would do to bring it back down. So we can say in general, when something's sitting up here away from equilibrium, we can say it's storing the energy. It's just a prediction. We're saying I did all this work to bring it there. It's good. Gravity's going to do all this work to bring it back. It's got to be the same amount. So I just know in advance, in the middle, I can just say it's storing it as potential energy. So potential energy from now on, potential energy is not just some formula. Every different conservative force has a different potential energy function associated with it. And the three that I named, by the way, are not the only conservative situations in the world. It's just like the three that we deal with in this class. So for any conservative force, the potential energy function associated with that force is what's written here at the bottom of the page. The work that the force would do, the conservative force will do to bring the object back from some arbitrary spot, x naught, to the spot of x equals zero, the equilibrium, whether it's gravity or a spring or electricity, whatever. That's what potential energy is. Okay? So wait, I think I might have skipped. So I may have to make one more slide for you. So we're going to use, wait, I'm going to just, oh, yeah, okay. So I can say this now. I can say, and I'm back. That's off my teacher thing. Like now I'm back to, I would say if you're you doing the homework and you're in step 3 of question 4 of homework 1A, since it's the first time that we're saying anything about energy or work in the document, I would now say something like this. If all the forces doing work on a system are conservative forces, right, then the whole idea of a conservative force is then the total amount of the total amount of energy, all the kinetic plus all the potential at any one spot has to be the same as all the kinetic and all the potential at any other spot. I know you've heard this kind of thing a million times before. I know that, but I'm trying to say carefully and rigorously. I'm saying like work is a transfer of energy. So as long as our only forces doing work are conservative, whenever we lose kinetic, we can say we're gaining potential. That's what we're saying here, right? Where anytime we lose kinetic under the presence of a conservative force, we know we're going to get that kinetic back if we ever, reverse the round trip. So we're saying from now on, any displacement under a conservative force can be viewed as the first leg, the outward bound leg of a ultimate round trip. So on your way out, if you find yourself losing kinetic, you're just storing it as potential. You'll get it on the way back. We can't say that for friction or the normal force, or there's no such thing as frictional potential energy. But there is gravitational potential energy or spring potential energy, whatever. So the truism from now on is the total amount of kinetic plus potential over here under a conservative system must be equal to the total amount of kinetic plus potential over there. Any two spots, x1 and x2. As a problem-solving technique, what are x1 and x2? X1 is a place that you know something about, and x2 is the place you're solving for. What do I mean by something or solving? Specifically, we're going to use this whenever we have a speed to spot correspondence. Like if you know the speed at one spot and you're trying to find out the speed, the instantaneous speed at another spot, or you know the speed at one spot, you're trying to find out the spot at which another speed will occur, that's when you use conservation of energy. And you say the total of kinetic plus potential must be equal from place to place if all the forces doing work are conservative. So total mechanical energy, must be conserved. This is all under if all the forces are doing so, is conserved from place to place, from spot to spot, location to location, as opposed to from time to time. That would be a different concept. All right, so we're going to do it here. Okay, so we're going to apply that here. We're going to say all the potential plus all the kinetic over here must be equal to all the, but the question is, what is the potential energy due to the spring? Like, I mean, I know a lot of you know, either you knew it from last semester or you found it on the web, which is all fine, but like, where did that come from? Why? So here's where the conservative force doing work here in this situation is the spring force. So we need to know the potential energy due to a spring. So what do? We integrate. We calculate the work that so I'm at the bottom of the slide now, like the white integrals at the bottom. I have to integrate once and for all, integrate the spring force from some arbitrary spot x naught to the equilibrium. Like how much work would the spring do to get the mass back to equilibrium? So I'm doing that integral. So I'm plugging in for F is negative kx. So I'm plugging in negative kx as my force. I'm integrating negative kx dx. And I got rid of the vector symbols because it's a dot product. You remember from last semester, it's a dot product. So I kind of skipped a step here. I apologize. Technically, it's like F times x times cosine of theta between them. Like you have to look at the angle, but the angle is 0 degrees. So the cosine is 1. In other words, the force and the displacement are along the same axis, so I don't have to worry about the vectors anymore or anything like that. So I get the integral of negative x dx. So the integral of negative x dx means I could take out the constant. I could take out the negative x, right? And I'm just leaving this blank for a second for you. If you want to, I don't want to, it's 10 o'clock. We got a little time. If you want to please put in the chat, publicly or privately, what is the integral of x dx? Or really, what is this integral? I mean, okay, I'll give you one hint. I took out the negative k. I'll say this much. I can certainly get rid of that negative sign by going like this, right? I think I can flip the limits of integrate. Oops, sorry, I didn't do it. If I want to get rid of that negative sign, if I want to multiply everything by -1 to get rid of the negative sign, I can do so as long as I flip the limits of integration. So now I have this integral. So do you want to put in the chat privately or publicly? Maybe privately is better if you want, so it doesn't influence other people. What is if this were a math class now, even if you've lost sight of all the physics, what's the integral of x dx in a math class. Nice. Oh, okay. I'm not saying if it's right or wrong, but nice that I see a response in the public chat. Thank you. And you're totally getting points for that, especially for going public. Awesome. Oh, awesome. I see now slightly different answers. Very good. Awesome, awesome. And people going public, nice. And since I got three answers, now I got something in the private. Awesome, awesome, awesome. And I'm not saying whether it's right or wrong. So you don't have to be influenced. I mean, you can still awesome. I see a lot now, and every single one of you, please submit for points. Oh, interesting. Interesting. Okay, I'm seeing a lot of different responses now. Awesome. And I'm going to tell you in advance, like they're different. So some of them are right and some of them are wrong. This is a concrete question. It takes guts to answer. Remember, you submit your answer into the portal that says for right or for wrong. And then strangely enough, if it happens that you were wrong, there's another portal that says wrong, really wrong. You can literally submit that there also and get extra points for being wrong, as weird as that is. But I want to encourage you to like not worry about being wrong. So I got a ton of answers now. And they're awesome. I'm gonna say, if you're thinking something, if you're thinking something like, shouldn't the answer be one, which frankly, more than one person said privately, that's totally awesome. I understand why you're saying the answer is one, but you're thinking derivatives. You're going forward, if you did the power rule of derivatives, yeah, you'd get one, but we're going in the opposite direction. We're doing an anti-derivative, so to speak, an integral. So it's not actually one. Instead of lowering the power, we're raising the power and then dividing by that power, so to speak, right? We're doing the power rule backwards. So we would get, as many people in the chat said, x squared over 2. Well, I'll write it here. So very good either way. I'm like, we would get x squared over 2 because I raise the power and then divide by that number. And then a lot of people put plus C in the chat, which is awesome. Also shows you've been paying attention in calculus and you know what you're doing. But the plus C is if you have an indefinite integral. We actually have a definite integral here. We're evaluating, right, from 0 to x naught. So we actually can plug in and evaluate and get something like this, which is very similar to what most people said. And even no matter what you did, like submit for the portals. But I'm saying it's that. In other words, the potential energy, well, yeah. The spring potential at the spot x naught, the spring potential energy would be 1/2 kx naught squared. Or at the spot 5, it'd be 1/2 k5 squared or whatever. So if there's any question, definitely tell me. But so I think we just got the potential energy function for a spring. Is it true for all time? Yes. So do we have to integrate it every single time? No. If we're going to use it ever in the rest of this document, like now we've got it, we're good. But we want to make sure we understand where it came from in the first place. Okay. So now, and okay, quick sidebar too. If you somewhere in your homework, either under self-sufficient document or under step 3 GDP, or possibly other places, if you didn't get the maximum rubric number of points, it might be because you wrote somewhere that you wrote something like total mechanical energy or potential energy is 1/2 Ka squared. Now, I'm saying this just to be clear and not to shame anybody. If you look at your homework and anywhere you have 1/2 Ka squared, I'm not saying that's wrong. I understand what that is. I understand ultimately why it's right or why it makes sense. However, that would assume that there's a spot in the situation called A. If you want to say something about 1/2 Ka squared, and yes, we ultimately will in this class, but if you want to say something about 1/2 Ka squared, that must mean there's an A involved in the problem. This is where step 1 DFP comes into play. If you want to use an A, then you've got to define an A early on so I know what you mean by A. How do you do that? You put a label in the diagram for where A is. I know in my heart that many of you understand A is a letter for amplitude. Amplitude ultimately means the same thing as x naught. But there's no way of knowing that just by assuming it. I think you get what I'm saying. So if you're going to use A, you want to define it first. And the truth is, we both know if A all of a sudden just appeared in your homework, even though I get what it means, a random reader doesn't know what it means. And more to the point, I kind of know that that means we got something from the web that we just wrote down without really understanding what it is. We don't want to do that. Okay. Again, this is not to shame anybody. It's all a very fine line. Just fix it and resubmit it, and you'll get the points. But you don't want to just like randomly start saying things about A if there's no A being introduced in the problem. Okay, enough said on. Okay, so from now on, regarding spring oscillation, I'm watching the notes, we could say, and from now on in this document or whatever, we could say from now on at any one spot, x1, the total amount of 1/2 mv squared kinetic plus 1/2 kx squared, the potential, it must be the same. Like that total must be the same here and there, wherever here and there are. So this type of motion this back and forth cyclical motion of the mass on the spring, from now on, we're calling oscillation. Anything that is cyclical, repetitive, with some kind of pattern, we're calling oscillation. The truth is, this whole homework sheet is meant to launch us into a very specific type of oscillation, which is very important in physics and PChem and instrumental. Very specific type that we'll get to by the end of question 9. But in general, repeated motion is called oscillation. If it was under a spring, this yellow statement would now always be true for that spring. So now I'm really in step 4 finally. Again, that's a lot of talk. I'm not saying you have to say all of this in your homework, but I wanted to, you just anything that's new you want to make clear. But now I guess we're in step 4. Here, what are the two spots? The spots are x equals 0. Oh, sorry, I actually said those backwards. The two, I mean, they could be, but the first spot is a spot that I know the speed, and the second spot is the spot where I'm solving for the speed. Well, the first spot where I know the speed, I know it's 0. Like the initial displacement, or what many of you are calling amplitude of the spring, is 0. I mean, the speed is 0, so I can cross out that term. That's convenient. Similarly, the spot that I'm solving for, the equilibrium spot, the x there is 0, so I can cross, there's no potential energy there, so I cross that out. So I can say from now on, I can say for the, sorry. The lab formula sheet. Okay, wait, I'm looking at the direct chat. Hey, what I'm trying to tell everybody is it's not that anything is, especially if something is in an equation sheet of our class, I'm not saying it's not acceptable. But what I'm saying is if it's the first time it's being introduced, it's got to be explained. Like a lot of the equations in our equation sheets for the class, those are equation sheets for the exams and stuff. They assume that we've gotten, like, they're sort of a prediction of what we're going to learn in this class. And once we learn it, it's all fair game. But if it's the first time something's being introduced, it's got to be explained. I'm not saying that A is not legal to use. I'm just saying if just A just suddenly appears, or yeah, well, that's what I'm saying. If it just suddenly appears in our solution, but it doesn't refer to anything, like there was no A given in the problem. So how do I know what A means? And I'm not saying this critically. I'm just responding to something in the direct chat. I'm not saying you can't say 1/kA squared, but the truth of the matter is A is another letter for what we're calling in this problem x naught. It's sort of about consistency. Like we're calling it x naught here. You can change it, but then you got to tell me you're changing it. If you know, whoever you are, all of you. Do you see what I'm saying? The first time you, for example, also, I know in that equation sheet, and I kind of regret this actually, but there is an equation that has to do with cosine omega t. That's a true equation. I'm not saying it's illegal or false, but we've never said anything about omega. We don't yet. We don't know anything about what omega means or anything. So for the first time it gets introduced, either by me in the class or by you in a document, it has to be explained and show that you know all these things means. I think you understand what I'm saying. Okay, and you don't have to apologize. Like really, and I apologize. Like it's a dialogue here. That's why we just keep revising the homework until we're all on the same page. But okay, so what I'm saying here is, well, here is another example. I'm saying or here, even more specifically, I'm saying that all the potential at the end, at the amplitude position, at the maximum, at the initial displacement, all the potential there must equal all the kinetic at the equilibrium, because I've picked two special points for which a lot of things cross out, cancel. Like, well, Yeah, I think you get it. I'm saying the total amount of energy for this entire motion must be a constant. At any arbitrary spot, some of that energy is potential and some is kinetic. But the reason that all over the web they say something like total amount of energy is 1 FKA squared, what they're saying is your total is all your potential plus all your kinetic. But if we cleverly look at a spot first where all of the energy is potential, like at x naught, all of the energy is potential. So all of the potential you have there is all that's going to be distributed throughout this entire motion from here on in. So it's going to be so for this case, problem 4, I could say 1 FKX squared equals 1 FMV squared. What I'm really trying to say to everybody, and you'll see this clearly when I get to question 5 in a second, I'm saying the step 3, the law that's always true, is this thing in yellow right here. Is that all of your energy over here plus it must equal all of your energy over there. In step 4, what that turns out to mean for this case is all of your potential here must equal all your kinetic there. But it's two different spots. The problem, so that statement is true in this case, but if you see that statement on the web, 1 FKX squared equals 1 FMV squared, that looks like, to a lot of people think, that's just like a true statement in general. That's like a formula. 1 F potential equals kinetic. What I'm really trying to say, and I'll move on, is you don't want to memorize or believe that potential equals kinetic. Usually it does not. You'll see in the next question it does not. At any one given spot, the potential and the kinetic are not evenly divided. They're two random, they're not random, they're two different portions of the total amount of energy. This is a special case where we're comparing the equilibrium position to the initial position. So the potential at one place equals the kinetic at the other. Okay, I'm going to go. But anyway, so that's the statement there for step 4. So I cross out that 1/2, I solve for V, I plug in the numbers, and I get, okay, for my final answer, at x equals 0, at equilibrium, the instantaneous speed equals approximately 3.87 meters per second. Okay, so that's the answer for question 4. Okay, I'm looking, okay, so then we go to question 5. Now I'm going to go a little faster now. Question 5 is the exact same, or well, I mean, I'm assuming there's no, I'll pause for a second. If there's any questions on question 4, going once, going to, okay. Can I get a thumbs up if I can move on? Okay, thank you, Sarah. Awesome. And everybody else. Okay, and Kyla, and Lena, and Sharon, and Erica, and Lilani, and Cindy. Okay, so questions, thank you. Oh, and all of you, awesome. Okay, so question 5, it's the exact same question. It's the exact same question in tree. It just reversed, right? It's a speed spot comparison. It's asking for, it's now this time it's saying when it has a certain speed, 3 meters per second, what is the spot for that? So it's the same concept, sure. So I did step 1, step 2. So step 3, sure, is the same GDP as before. I mean, as the last question. I can cut to the chase now because I did all this heavy lifting to establish it. So, but what is that step? This is where I'm warning everybody. I wouldn't write 1/2 mv squared equals 1/2 kx squared. Honestly, that's what a lot of people end up writing for question 5. Think it is the same question. It does require the same universal statement, but the universal statement is total energy over here equals total energy over there. Now, when I go to step 4, I can cross out one of the terms. I could say over here at the initial position, there again, it's the case that there's no kinetic there. Fine. So I cross it out and call it 0. But the spot I'm looking for, x, this is my key point. The spot I'm looking for, x, there's potential and kinetic at x. There's potential because x is not 0. It's somewhere in the stretchiness of the spring. But the thing is still moving as well. It's moving at 3 meters per second, I was told. So there's both types of energy at this arbitrary spot I'm looking for. So, so I can't cross out both of the terms like I could before. Do you see what I'm going to move on, but I'm just trying to say this is the difference. And this is what sort of the thinking of physics gets involved is there's a big difference between a step 1 and a step 3 and a step 4. The truth here is that total mechanical energy is conserved. the sum of kinetic and potential. Then I can cross out terms as applicable or not. And when I do here, I've just crossed out one of the terms. I can cross out all the 1/2s, that I can do. And I'm solving for X. I'm solving for the X that is unknown, the X where V equals 3. So I rearrange everything for X. Again, it's good practice to plug in the numbers at the last minute. Try to practice that now when it's a little bit uncomfortable, but not very anyway. So I plug for it, and technically, I'm going to get two possible answers, right? Because the question just asks, where, at what position is the speed 3? It doesn't say the velocity is positive 3. Not trying to be technical, but I am being technical. It just says when it's going 3 meters per second fast. Well, it could be on its way in, or it could be on its way out. I mean, it could be during an expansion, or it could be during a compression. So mathematically, it's like saying, well, I'm thinking of a number that I'm thinking of a number that when you square it, you get 9, for example. Well, that could be positive 3 or that could be negative 3, right? So there's two. No problem. Thank you for the chat. Got it. Thank you. Appreciate it. Hello. So the answer is plus or minus the square root of all that stuff, and you get plus or minus 0.095. If you did it a slightly different way, but got the same answer, as long as you understand your way and you explained it, that's great. I mean, there are slightly other ways to, but if you did it a slightly different way and didn't get this answer, it's probably because you said 1f(kx) squared equals 1f(mv) squared, just like you said in question 4. I'm trying to emphasize that's not the truism here. But anyway, that's the answer, plus or minus 0.095 meters. So at either one of those places, the speed will be 3. Maybe at one of those places, the velocity will be negative 3, but the speed will be 3. So that's the answer to that. Sorry, any questions? Okay, I'm going to move. I know we're good. My goal is to get to question 9, as you can tell. So so now, from here on in, because I'm trying to get to question 9, and I hope this doesn't I think I'm showing you enough about how I do the grading and the expectations, and I'm showing you how to do the steps. And I will often keep doing the steps in class, but sometimes if I just want to make tracks and get to answers, I'm just giving you, so you still have to do the steps, but I'm skipping them right now for these notes. So question 6, for example, it says, how far does it go on the other side, basically? If you just in your gut intuitively felt like it should be negative 0.15, like it should go the same amount, you're totally right. It's not a trick question. The answer to question 6 should be negative 0.15. But I'll tell you this. The reason that it says it in blue. The reason that you just intuitively feel that it sort of should be the same on both sides is because that's the intuitive sense of energy conservation. Once you believe something is conserving energy, it means it's symmetric in time like that. If there were non-conservative forces doing work like friction, we wouldn't believe this. But since all the forces doing work are conservative, yes, it's totally true that the answer should be negative 0.15. And frankly, if this were an exam or something, the way you would show that is you would literally realize this is the same question again as question 5. Question 5 said, find the spot where speed is 3. So you did a bunch of math and you technically got 2 answers, positive 0.095 or negative 0.095. Well, this is really asking mathematically, find the spot where V is 0. And if you work out the same math that we just did a minute ago, but you solve for when V is 0 rather than 3, you'll get 2 answers, a positive and negative root. And the 2 will be positive 0.15, which we already know, and negative 0.15. In other words, it still is, it's not just like a guessing thing. The math of energy conservation will verify your intuition about energy conservation, that it should be symmetric. And similarly then, question 7, when it says how many cycles, how often should this, for how long should this process go on if energy is truly conserved? Which, it's hard to perfectly conserve it in a lab, but the better the lab is, the better the equipment is, the longer the spring is, the tighter the spring is, the more uniformly tight, the more close we will get to this truth. And we can eventually get to a reality that is only imperfect to levels that we can't even measure. I didn't say that well, but what I'm trying to say is if you really believe any amount that you believe these numbers, 3.87 or 0.0195 or then you can believe that what we're saying is, okay, it's starting at 0.15, it's starting with this amount of potential. It'll go until it has that same amount of potential on the other side. That, but energy is conserved, so it should go back to that side again. There's no reason that that process should stop if the energy is truly conserved. If you believe the prior numbers of question 4, 5, and 6, then what that says is the thing is going to keep going on forever. Is the is the spring in our lab really going to go on forever? No, it's not that great of a spring. Could a lab with a lot more money or, government funded at MIT or whatever, could they come up with a spring that goes on longer than we have the ability to measure it? Yes, which is what infinity means to a scientist. All right, question. So I think I'm looking at the chat. Okay. Now, question 8, I kind of want to do, we still have 20 minutes. Okay, question 8's a little deeper. It asks for the first fourth cycle of this oscillation, from just amplitude to equilibrium, what is happening to the magnitude of various quantities? It asks, well, what it asks for, I can't cover, wait, can I do this? Yes, what it's asking for is velocity and acceleration. It's asking for the magnitude, like what's happening to the magnitude of velocity on the way in, what's happening to the magnitude of acceleration on the way in, right? Well, velocity means like the first derivative of position with respect to time. Acceleration is the second derivative of position with respect to time. Then it asks about the third derivative, jerk. Now, we've never thought about that before in physics 203, but it's just the next derivative. We're going to start thinking about it now. But that's hard. Like, how do I know what the jerk is doing? Maybe I could figure out the velocity and acceleration, but can I figure out the jerk? Well, one hint, is that maybe look at pattern recognition. I could back up. So it says, sorry, this is not readable. It says, hint, in order for answering this hard question about jerk, maybe back up and look for pattern. Now, unfortunately, I've already written the answers here but very quickly, if I look at now I'm not trying to trick anybody. If you look at the position, I'm just going to do this quickly. If you look at the position, it starts at, and we're only looking at magnitudes. We're looking at trends in the magnitude of these. Oh, so sorry. I don't know if I just said this clearly. So it's asking us about derivative number 1, derivative number 2, derivative number 3. Why don't I back up and just ask myself, what's the function doing in the first place? So what's the position doing? It starts off at a position of 0.15 meters, what many of you are calling the amplitude, correctly calling the amplitude. It starts off at 0.15 meters and it moves to 0. So the positions, no trick question, the positions are decreasing from 0.15 to 0, like, right? So I could say, it's not meant to be a trick. I'm looking for a pattern here. Hello, hello, hello. So the positions are decreasing in that first quarter of cycle. Those speeds, the magnitude of velocity, well, it started off at 0 speed and it went to 3.87 meters per second. So the magnitude increased on the way in, like it's getting faster and faster as it goes. The acceleration, however, is going down. It starts, if you look at your homework, if you look at your answers to the homework, it starts with a really big net force, a lot of potential energy on this mass. It's being pulled really hard in. The net force divided by the mass gave you a number of negative 100 meters per second squared. Huge amount of acceleration right at the beginning. Now, I don't care about the negative sign. That's just saying that it's being pulled in toward equilibrium. That's not, the point is it's a huge magnitude of 100 meters per second. By the time it gets into the center, it's not accelerating at all. There's no net force on it at equilibrium. So the acceleration magnitude goes down from 100 meters per second squared, an absolute value of 100 meters per second squared, to 0. The acceleration goes down. Now, you may want to privately think about that. I'm going to move on in a moment, but I'm asserting that while this mass is coming in, it's getting faster and faster. But it's accelerating, it's moving in, getting faster and faster. So it's accelerating, but its rate of acceleration is going down. That is interesting. I mean, I think. I mean, that's euphemism for it. That might be confusing to you. If you are slightly confused by that because you're actually listening to me and you're actually thinking about it, good for you. I mean, it is right. I'm not trying to confuse you. But you may be just still getting used to the idea that acceleration and velocity are not the same thing. The speed is increasing, therefore, the object is accelerating, but the rate at which the speed is increasing is decreasing. What? I'm saying, imagine a pile of speed. The pile of speed is getting bigger and bigger because you keep adding to the pile. But the amount that you're adding to that pile is getting smaller and smaller. It's like like 8 slices of pizza, then 6 slices of pizza, then 4 slices of pizza, then 2 slices of pizza, then one, right? So the amount of pizza is growing, but it's growing by less and less. That's what's happening here. The thing, as while the thing goes in, its kinetic energy is going up, i.e., its speed is going up, but the rate at which it's doing that is going down. The acceleration is going down. Yes, yes, that's good, Tree. I'm going to keep going, but I see what Tree wrote in there. This is like a Zeno's paradox thing. Yes, very good. That's a huge connection. I'm not going to rabbit hole, but yes, good for you. So you may in private want to think about that. Velocity, anyway, but it's the case. Something can speed up while its acceleration goes down. So now we get to the last one. What about the rate of the rate of the rate? That's a new concept. It's a little bit head spinning sounding. Well, just looking at the pattern, if I had to guess, I would guess that the rate at which the acceleration is going down is going up. That's what I would conjecture. Looking at the time, we got 15 minutes. And I'm just guessing because it seems reasonable. Does that mean I'm right? No, that doesn't mean I'm right, but it means I have something that I can look at now. This is important. I'm setting the stage for the very last question. It's okay in science to guess, to make an educated guess. In fact, that's really the art of science. That's how science pushes forward. It always starts with an educated guess, a conjecture. But what makes it scientific is that once we have something to work with, once we've got something to consider, then we've got ways of testing whether we're right or wrong. Let's look at this conjecture for a real quick minute. Like, can we verify? I'm conjecturing that the jerk is going up since the acceleration is going down. In other words, I'm conjecturing that this pattern is going to keep going. Can I verify? Well, look, the net force on this thing is the only force on this thing is negative kx. Hence, that's the net force. So negative kx equals ma. So I substitute in a means the second derivative of position with respect to time. I'm saying, and this is the important statement here you're going to want to use. Oh, sorry, for question 9. Like I'm saying, according to F net equals ma and Hooke's law, I'm saying this is true. But if you look at that's a very deep remark. That means acceleration. It means the second derivative of position is directly proportional to the position itself. If the position going down, the second derivative is going down. They're doing the same thing. They're not the same number. They're doing the same thing. They're directly proportional. If you double one, the other gets doubled. If one is negative, the other is negative. If one is positive, the other is positive. You see, right? They're trending in direct proportionality. Well, if that's true, I can take the derivative of both sides. Yeah, look all the way at the bottom. In the middle, I just said in English what I just said. But I can take the derivative of one side if I want, as long as I take the derivative of the other side, as long as I do the same thing to both sides. So if I'm looking for jerk, he's right here at the front of the Zoom. If I'm looking for the jerk, I want to take the derivative of the left side of the d2x, right? I want to take the derivative of this to get the third derivative. So I take the derivative of the other side as well. But the derivative of the other side, the derivative of x is dx dt, velocity, right? So this says, if you take the derivative of both sides, it says the pattern continues. Whatever the velocity does, directly proportional to that is the third derivative, the jerk. If the acceleration is directly proportional to position, then the jerk is directly proportional to velocity. Because if I take the derivative of one side, I have to take the derivative of the other. So it says whatever's happening to velocity must be happening to the jerk. It says the pattern does continue, and that will go on forever. In other words, what makes oscillation of this kind interesting and worth studying and worth getting to question 9 it's on the one hand, it seems really simple. This thing is just going back and forth and back and forth. And it seems like a really simple equation. F equals negative kx. Like it seems simple. But what we're realizing now is that when something goes back and forth forever, it's not just the place that's going back and forth. It's not just that the place is going down and then up and then down and then up. I mean, in terms of values on a number line. It's also the speeds are going up and then up and then down. But also the accelerations are going down and then up and then down and then up. And in other words, it's not if there's something goes back and forth in this simple pattern, it has derivatives forever, all going back and forth and back. There's no, unlike free fall, where we say, oh, something's falling, it changes its position, therefore it has velocity. It changes its velocity, therefore it has acceleration. But when something's free falling, its acceleration is a number. All the derivatives after that are zero. We stop at the second derivative level in physics 203 with something like free fall. We do constant acceleration. Here we have this motion that's not so exotic. It's not crazy. It's not like a black hole or something. It's just something going back and forth and back and forth. But apparently something going back and forth and back and forth has derivatives alternating forever. There's nothing about this that's constant, it seems. Nothing kinematic about it that's constant. So when we get, so that's good to have in the back of your mind. So when we get, so we just verified that the answer is that. So if we get to question 9, okay, this just says you can write, this just says what I just said in English. So we get to question 9 now. We ask a question, we have 9 minutes left, which is fine. We ask what seems like a simple question. Okay, so like when the object is at, I'm sorry, when the clock strikes 1, when we've let 1 second go by, where is this mass? It seems like it's a completely reasonable physics question. You name the time, can I name the space, the place? Well, it seems simple, except normally the way we would get that answer in physics, normally we would say, well, if I know the acceleration, if I have some constant thing like a constant velocity or a constant acceleration, I'll be able to predict. But here, what we just established is the acceleration. If you want to know the position, you'd think you need to know the acceleration. But in order to know the acceleration, you need to know the position. I mean, that's what this thing over here says. Well, this thing over here says. So something is interesting here and new. When it asks in question 9, what is x for t equals 1? What we're really saying is t1 is just an arbitrary example. There's nothing special about the first second. I'm just using that as an example. What we really seek, as it says in the center of the slide here, is how does x relate to t in general for an oscillator like this? We're looking for a function now. This is one of the reasons I emphasized step 3 GDP so much is I know for a while in physics, it seems like you got to solve these problems. So you need functions and formulas to plug in to solve the math. What physics is really about is coming up with those equations in the first place. They came from somewhere. They make sense. We need to derive, we need to figure out what is the function, the position function that allows us to predict where something is in time if it's obeying Hooke's law. That's the goal here. So the goal is really what is x, and you want to bear that in mind for the next 7 minutes, but also really for like the next 3 weeks. The goal here is what is the x function of t under this particular condition? What is the particular condition? Hooke's law. So our step 3 is we got f net equals ma as always. We got f equals negative kx, Hooke's law. And also we're reminding ourselves now under step 3 that the definition of instantaneous acceleration is second derivative of position with respect to time, right? That's a GDP. A means d2x dt squared. Okay, so I plug in, now I'm up to step 4. I just do the same thing I did over here in question 8. I'm just, plugging in Hooke's law on the left side, blah, blah. So I get negative kx equals m d2x dt squared. And then I just rearrange a little bit the thing that's intimidating about this is the derivative. So I just get it by itself. And I say, what I'm looking for here is some x. I'm going to keep saying that. We are looking for x, not such that we're looking for some kind of function, some x of t, such that if you take 2 derivatives of x, you'll get back x times some constant times -1, right? That's what this bottom line says, is we're looking for some x such that its second derivative equals x times a constant. I mean, in other words, times k over m times -1. That's a mouthful, but we're looking for we're looking for some kind of position that when you take two derivatives of it, you get back position. In other words, the acceleration is based on position. I mean, of course, the position is based on acceleration, but the acceleration is based on position. That if that sounds circular or weird, yes, that's why this is a very unusual, interesting, new type of equation. Do we want an x? We've got 5 minutes left. We want an x such that when you take two derivatives of it, when you take a derivative and then a derivative again, you get back x, but times like a constant, k over m, times -1. Well, so how do we do this? It doesn't matter whether we're the most advanced mathematician in the world with the most experience or the most advanced physicist, or we're the physicist who's seeing this for the first time and has to figure it out. No matter what they do is they conjecture and verify. There is no straight line procedure for this. There's no algorithm. You have to guess based on experience and reason. And if you're more advanced, you have more experience to guess. If you're less, you have less. But no matter what, you're conjecturing and verifying. How could I possibly conjecture this? Well, I'm a physicist. I've been in the lab with you. I mean, you've been in the lab. You've already looked at a mass going back and forth on a spring. If you're looking for a function, picture the graph, like Desmos or something. Like, picture something's going back and forth in time. Or if I make... Oh, sorry. This slide just says what I just said. I'm going to move on. Well, yeah, I'm going to move on. So we're going to conjecture and verify. If I picture this, if I put time on the on this axis and position on this axis, I picture something that's going back and forth, starting at a value that isn't zero, going towards zero, then going past zero, going all the way down, and going back and forth smoothly in time, for which all of its derivatives are smoothly going back and forth, back and forth. So the simplest possible function I could guess to capture something like that would be a cosine function. That doesn't mean it's right, but I'm going to always start with the simplest thing and then see if it works. So I'm going to guess cosine. Also, I know from math class, if I take the derivative of cosine, I get negative sine. If I take another derivative of negative sine, I get negative cosine. Oh, that means that's a function that if I take two derivatives of it, I get itself back times some constant times negative. That's sounding good. It doesn't prove it, but it's sounding good with 3 minutes left. So I'm going to conjecture, and this is what you would write down the first time you establish this in a homework or an exam. You'd write down conjecture cosine based on these reasons. So I'm going to, but I am a scientist. So I'm guessing it's some kind of cosine, but I'm a scientist. There's units involved. These are measurements. They're not just random numbers. So the units of time are seconds. You can't take the cosine of a second, period. You can only take the cosine of something measured in degrees or better, radians. So there's got to be some number before the seconds that cancels out those seconds and leaves us with radians. There's got to be some constant, right, before the t that multiplies the t. So I'm going to guess there's some constant there that's measured in radians per second. I could call whatever I want. I know all over the web they call it B or A or something like that. You can call it whatever but establish it. I'm going to call it omega to save time because that's what other people call it. Similarly, when I take the cosine of a radians, I don't get something in meters. I just get a raw number between 1 and -1. But I know my answer has to be someplace in meters between like the initial position, 0.15 meters, and -0.15 meters. So I'll multiply the whole thing. I'm going to guess that the whole thing is multiplied by some constant measured in meters. I'm going to call it x naught. So I know I'm doing this fast, but I'm putting together a guess based on experience with mathematical functions with the lab and with units of measurement. So my guess is x equals x naught cosine omega t. I'm guessing that. And yes, it's in the sheets stuff. How can I verify? How can I prove it's right? I take two derivatives of it. The whole issue, and I know we only have 1 minute left, but we're just about there. The whole issue is x needs to be such that if you take a derivative and you take another derivative, you get negative k over m times x. So very quickly here, you can look in your notes or repractice on your own. If I take a derivative using chain rule and trigonometric derivatives, you'll see what I got here. If I take another derivative, I get back negative omega squared from chain rule doing twice. I get negative omega squared x naught cosine omega t. So what? We're just about done. So what does that mean? But x naught cosine omega t was what I guessed x to be, right? So I literally just said if I take two derivatives, I get negative omega squared, whatever omega is, what omega times x. So what? Well, what I was supposed to get, I know I'm going fast. You'll look at the notes later, but we're just okay. What I was supposed to get was negative k over m x. What I got was negative omega squared x. But omega was just a placeholder. I didn't know what it was. I just knew it had to be measured in radians per second. So as long as that omega squared means k over m, then I have my answer. As long as omega squared is k over m, then the cosine guess verified. So the answer is, and we're done. You can put down the cannoli. The answer must be an answer that works, that solves this differential equation is x equals x naught cosine square root of k over m t. I just guessed it and then I verified it. So in general, that's true. We can now establish that for the rest of time. Now, if you have that differential equation that describes Hooke's law, then a solution is x equals x naught cosine omega t, where by omega, what I mean is square root of k over m. So if you plug in the numbers for this particular case, you get 0.116 meters as your answer. I'm done. That's your answer. But what I'm really trying to tell everybody is the 0.116 meters is just a particular example. The real issue is we just showed that the position can be predicted for any time on an oscillator if we use the cosine function omega t, where omega is the square root of stiffness over mass. That's what we just showed, and we'll continue that. Great job, everybody. We're done. Have a great weekend. I'm going to turn off the recording, but I'm here if anybody has any questions, and I'll be in my office Monday. Blah blah blah. Okay. Okay.
Hi,
Have a good
Professor.
day. Yes. Have a good day.